me briefly recall what happened last time. So we have Lagrangian classical theories. And main examples were classical mechanics, second and first order, nonlinear sigma model. So let me just briefly, since I've mainly focused on the scalar field, so let me repeat how it works for general X. So in this case, fields are maps from M to X, where X is called the target space. Both M and X are Riemannian. So dphi, it maps tangent bundle of M to tangent bundle of X. So dphi X can be considered as an element of Tx star M tensor T phi X X. And because they are both Riemannian, on this vector space there is a natural scalar product. So this is exactly the kinetic term of the nonlinear sigma model. So this is the Lagrangian, and then you can add the potential function. It would describe the self-interaction of this scalar field with itself. So and then the action is the integral of the Lagrangian with respect to the Riemannian volume. Okay, so the next example was the Yang-Mills. So in this case, fields are connections on a principal G bundle. So I do not have them A, and let's just assume for simplicity that P is trivial. So in this case, A is a one form, can be considered as a one form on M. G valued one form on M. So the action is the integral of the trace f of A. That's the way how we defined it last time. But then M is the Riemannian. So this is the Riemannian volume form. This is the scalar product of two forms, and trace is the killing form on the Lie algebra. So, but because M is Riemannian, so there is an actual operation that's known as Koch star, and this operation is induced by two things. First, the natural pairing between I and n minus I forms, simply the integration over n. And second, the natural pairing on I forms are given by the metric. And in terms of the Koch star, the action can be written as 1/2 trace f of A which star f of A. So in this case, see that f of a is two form, star f of a is n minus 2 form, the wedge product is n form, so you can integrate it over n. So, and then the next example was Chern-Simons. And you see, in order to define this action, you really need a Riemannian structure. So I'm just repeating the last lecture for those who came later. So this is the nonlinear sigma model. Just fields are maps from M to X. Both spaces are Riemannian. So the differential is the map of tension bundles. So it can be a point X can be considered as an element of this vector space, which has a natural scalar product. So that's the Lagrangian, and that's the action. So then the next example, again, it uses the Riemannian category, and then Chern-Simons doesn't use Riemannian category, so in this case the space-time is just stated from the topological category. It's three-dimensional. So fields are connections in the trivial G bundle over M. And again, because of this, they can be thought as one forms on M with coefficients in G. And then the action is simply 1/2 integral over M trace A wedge dA. Now, after taking trace, which means that we take the Killing form of this, of the tensor product of these elements of the algebra. And so with this is 3 form, and then another natural 3 form is we take A and take its top exterior power, and this combination is special. It's a 3 form, and it's special because it is gauge invariant modulo Z for closed. And in this case, the Yang-Mills action is just gauge invariant. In both cases, G is an element of the gauge group, so the group of bundle automorphisms. And in the case of trivial G bundle, this is simply smooth maps M to G. And the gauge action is AG is G inverse AG plus G inverse DG. And I assume here that G is a matrix group. So both G and G are subspaces in n by n matrices, so you can multiply elements of the Lie algebra and the Lie. Just for simplicity. Of course, you can do it in general case, but sort of then this would be sort of some construction from the Maurer-Cartan form, and this would be the adjoint action of the group on the Lie algebra. Okay. So then we pass to the Hamiltonian field theory. So we had the data and the axioms, and then we have 2 examples. And if I remember correctly, I stopped just before describing the Hamiltonian structure for the scalar field. So the first example was Hamiltonian formulation of classical mechanics, second and first order, and we have seen the difference between the second and first order classical mechanics. In this case, the symplectic space that we assigned to the boundary was the Cartesian product of two copies of the cotangent bundle for n with different signs of symplectic structure. And in this case, it was m cross n, but again with different signs of symplectic structure. And of course the symplectic structures were different. This omega is d alpha, where alpha is the first order term in the Lagrangian, the magnetic term, and this omega is just the standard form on the cotangent space. Okay, so now let me briefly go through the infinite dimensional examples, and then we will pass quickly to the discussion of quantum field theory. The truth is that although I like very much the Hamiltonian formulation, and I like very much the quantization of this Hamiltonian formulation, because this is something that's sort of mathematically more sensible than quantization of the Lagrangian formulation. But this time I want to focus on the path integral quantization of the Lagrangian formulation. So in some sense the Hamiltonian part is somewhat decorative here. So the only constructive part of the Hamiltonian picture is the discussion of boundary conditions, which will be important for Chern-Simons, but that we will do later in the course. So, but now let's look at the other examples. So the nonlinear sigma model. Again, let's just for simplicity consider the case when x equals r, and it's a good exercise to generalize this discussion to the general case when x is a Riemannian name. So the homework, which will not be graded, sort of volunteer homework, generalize, do this for any Riemannian x. So, so in this case, I will just give the answer S dm. It's a so now it's this Lagrangian is the space, is the cotangent space to the space of maps, smooth maps phi from dm to r. So this is the cotangent space to the boundary values of fields. And the Lagrangian subspace in this case is the, well, let me introduce, so this is really an infinite dimensional vector space, and we are talking about the cotangent bundle to an infinite dimensional vector space. So let's introduce here the coordinates. So if phi is the boundary value of the field, then p will be the corresponding coordinate on the cotangent direction. So this is the cotangent coordinates, and these are the coordinates on the boundary values. So Lm is the space boundary values fields such that Px is equal to the normal derivative of a classical solution, and Px is equal to the classical solution, where phi c is defined on M, and it is a classical solution. It is a solution to the Euler-Lagrange equation. So in other words, this Lagrangian subspace is the space of boundary values of solutions to Euler-Lagrange equation, but Euler-Lagrange equation of the second order. So on the boundary it defines not only the boundary value but also the normal direction to the but also this thing, this is normal direction to the classical solution. So this is the subspace in S dm, and that's the Hamiltonian structure. And then you can also, and there is an unfortunate thing that I noticed only now, that the symplectic manifold assigned to the boundary is denoted by the same letter as the action. So let's just assume that there is no controversy about it. That say these S's, although they look different, we'll understand that they mean something completely different. And I noticed it because I want to write the variation of the action in the next formula. So this S clearly is different from this S. So, so this is the action. And then if you will just compute the variation, you see there is a term that involves the derivatives. And when you start to vary this term, there will be d of variation. But you want to get rid of such terms. You want to have the variation just as the tangent vector to this space of fields. So you use the integration by parts. When you use the integration by parts, as we discussed it last time, there will be a boundary term, and the boundary term is the integral over the boundary dn phi delta phi dx, where this is the Riemannian volume form for the boundary minus the integral over m, and then delta phi plus d prime phi delta phi dx. This is the volume for n. So Euler-Lagrange equations, we guarantee that this term is vanishing. And now if you look at this term, so we can see that delta S phi on solutions to the Euler-Lagrange equations, it is equal to alpha delta phi restricted to L, where alpha, well, maybe I should say theta, where theta is the canonical one form for the tangent bundle. So in other words, this symplectic structure that we have on S is equal to d theta, where d is the differential in fields. So this is sort of so this is the picture, and then from here we will have a longer discussion. We can sort of deduce what sort of boundary conditions we should impose. So now let me skip this discussion because I want to go as fast as possible to the discussion of the Feynman integrals. But we will return to this. So this point can erase.
Maybe it's not so important, but when you say cotangent space, I mean these are functionals of the vector space. I mean you have the cotangent space of a vector space.
Yes.
So is there some topology here or some?
All these spaces are infinite dimensional. So
right.
If you really
so topology matters.
So in some sense, say when you say a dual to an infinite dimensional vector space, a much more sort of handleable notion is not the notion of the dual in some topology, but just the notion of a pair of infinite dimensional vector spaces with non-degenerate pairing.
Okay.
And then you can complete it, and then you can get topological dual. So in this case, so if you have so these are the coordinate functions. So if you have a vector field on this manifold, so then that would be the thing. So that's so if this is the tangent, so this is the tangent and the x, this is an element cotangent and the x. The pairing between the tangent space and the cotangent space is simply this.
Yeah, so what is the cotangent space? Before you do that.
Well, with respect to this pairing, you can say that the cotangent space is simply the space of maps from M to R. So all these spaces. So it's like if you have Rn, then the cotangent space to as well as the tangent space, any point.
So I identify the tangent space with the cotangent space, and then you define this diagram.
Yes, exactly. And this pairing is simply the Euclidean scalar product. Okay, but I still need an eraser. It's here. So just let's leave the discussion of the Hamiltonian structure of the Young-Mills theory and of the Chern-Simon theory to the later days. I just want to give the answer to an exercise that I gave yesterday. I mean, to find the boundary term in the variation of the Young-Mills theory. Who did this exercise? Only one person. Okay. So let's do it together. So, well, for this, it's more convenient to write it in terms of the Hoche star. So we're talking about the variation of A star and A. So now f. So in some sense, I'm skipping the first part in the Yang-Mills theory, and I'm kind of focusing on this part. And it will be a while before we'll come back to the Hamiltonian picture. So everybody is welcome to try to just use this example, which we discussed now, and to formulate the Hamiltonian picture for the Yang-Mills theory. And then we'll compare the notes. So, so f of a is dA plus 1/2 a wedge bracket a. I defined it last time. So you see, when you vary the first term, you will have d of the variation, and that's where you have to integrate by parts. When you vary the second term, you don't have such thing, so you shouldn't worry about it. So this will be integral over n trace delta fa wedge star fa. This is because this product is symmetric, and if I vary this, I'll get one copy of this expression, and if I vary this, I will get another copy of this expression. So this is at this stage we eliminated 1/2. So now in this expression we have, this is d delta a plus delta a wedge a bracket. So when we integrate by parts, we will have, so first of all let me write the term where we have to integrate by parts. Trace d delta a wedge star f of a. This is where we have to integrate by parts. Plus integral over n trace delta a wedge a wedge star f of a. This is where we don't have to integrate by parts. So then let's see. The result of the integration by parts will be, we have to integrate something over the boundary, and for this, in order to understand what is this, we just have to use the Stokes theorem, and it says that this is delta a wedge star f of a. So this is, so if the dimension of M is M, F is 2 form, star F is n minus 2 form, delta A is 1 form, so this is n minus 1 form. But now we should take the sort of tangent part of it, because we're integrating by parts, so now we're integrating over the boundary. And by tangent I mean the top exterior power of this form on M may contain the normal directions. So we take the only monomial from this n minus first exterior, n minus first form, we take only one monomial that doesn't contain normal directions to the boundary. That means tau, tangent direction. Minus the integral over M trace, and then we'll have the delta A d star fa. plus this term. So altogether it will be integral over the boundary, trace. I will not do yet anything with this expression. So it is still the tangent part of this n-1 form. This is the n-1 form on M. And we take its tangent part at the boundary. Minus, and then if you think about it, you will convince yourself very easily that what is written here is simply the covariant derivative of star of A. And this is, so this is n-2, this is n-1 altogether, this is one form, so it's n form, we can integrate it over m. Okay, so then from here we conclude that Euler-Lagrange equations are dA star fa is 0, or sometimes it's convenient to introduce the Hodge-dual differential, the one that's responsible for example, for divergence of a vector field. It acts in the opposite direction. It acts from I form to I-1 form. And then the just take one more star from here, and this is the same thing as so these are the Young-Mills equations. Okay, so now we have to focus on the boundary term. And just let's look at what is this. Yes. So we should take a monomial which doesn't have any normal directions. So if we have an here, that means that we have one normal direction. So it's impossible. So here we should have the tangent direction. So this is already one form on the boundary. So then we should have, so this is still the expression that's, so this is still on M. And then we take the boundary component of it. So remember what F is. F is dA plus 1/2 A wedge A. So I claim that what's written here is the following. It's the Hodge star for the boundary. You see, the boundary is also a Riemannian manifold. It has a metric, it has its own star operation, which maps I forms to n-1 minus I forms. So from an I form, this will produce n-1 minus I form. We already have 1. So what we need here is n-2. So which means that we should apply this operation to a 1 form. So how can we get from the curvature, which is a 2 form on M, 1 form on the boundary? Well, one of the components of this form should be normal. And so F tau n A. And now what is F tau n? It's a one form on the boundary given by the normal derivative of the restriction of A to the boundary of the tangent component of the form minus the Ram differential in the tangent directions of the normal component of the connection at the boundary. And this is a function. It's a function on the boundary. Plus, and then it's tau n, so it's a tau a n. Good bracket. So so what is written here is the covariant derivative with respect to tangent component of the connection of the function a n. This function is not scalar valued, it's Lie algebra valued function. So this is why we have the U bracket. And so finally, the variation of the action on solutions to the Euler-Lagrange equations is equal to the integral over the boundary trace delta, and then I can either use the star notations again, or I can use the scalar product. So I mean, in this case I prefer to use the scalar product. A tau dn a total component. So I wrote something. Well, what is written here is the normal direction. It's a normal derivative of the tangent component of the connection in the vicinity of the boundary. We can, using the metric, we can split the connection into normal and tangent directions near the boundary, then take the normal direction and then restrict it to the boundary. So it's a bad notation, but this is what it means. Tau minus dA tau a. Okay, so this is the solution to the homework exercise, and later we'll use it to see better the Hamiltonian structure in the angular state. So something that's left as a sort of philosophical exercise, philosophical in the sense that you can figure it out using this examples, but it's not going to be trivial. So if you fail to do this, it's okay. We'll discuss it later. But it's a great idea to try. So, any questions about this part?
Yeah, I'm still not entirely sure. In the formula you have at the top of the node bracket, so what exactly do all the terms mean? So A is a one form on
yes
on M.
Yes. So
Now you restrict that to the boundary.
well,
and as the boundary is split it. Is that what you do?
I take the infinitesimal neighborhood of the boundary, and
so there's some color of the boundary.
Yes.
For that, yeah.
and I split it in the
In the color
infinitesimal neighborhood, in the color of the boundary.
to split it. So now we have two one forms. So what is dn?
So this form I will write as dxn, I suppose.
Yes. Okay.
Yes,
So an is a function and a tau is a one form.
Yes, exactly.
Okay.
Yes, so that's what I meant by writing the derivative. So I suppose that I should have written it like this. dx. That would be long. It's a two form. One direction is normal, the other. It's the component of these two forms where one direction is normal.
And the first normal, the first delta n, what does that mean exactly? So there is a tau is a one form.
What is it?
The first term, the delta.
This one.
No, in the parentheses. The delta n.
This one.
Yeah. So what does delta n mean exactly?
It's the derivative of the. So in the color we have the normal directions. So this is the derivative with respect to the normal direction.
You do dxn.
Yeah.
Yeah.
Okay.
dxn, yes.
Yeah. Okay. So it's still a one form.
Yeah. Yeah, this is the one form in the tangent directions. This gives the one form in the tangent directions. This is the one form in the tangent directions, and then you wedges with the dxn. That would be the right.
Very good. Then I can understand.
So, yeah, so in this case it's one form in the tangent directions, and this case it's one form in the tangent directions. Okay, so let's make a break, and then we will have the quantum field theory after the break, and then we will return to the Hamiltonian picture. So I will start to discuss quantum field theory not from the Hamiltonian point of view, but then we will have a discussion of the Hamiltonian.